Hello everyone, my name is Nathan Semertzidis, and here I will be presenting our wearable brain-to-brain interface system named PsiNet, and our efforts to evaluate PsiNet and investigate its user experience. So, to begin, brain-computer interface is a term that describes a class of technologies that provide a direct channel of information exchange between the human brain and the computer. So, largely this involves reading some form of signal from the brain, such as, for example, electroencephalography. And more recently, we're just beginning to see more advanced BCI that also enables the computer to send information to the brain via some form of brain stimulation. Recently, there has begun to be a growing interest in brain-computer interfaces, both from the lay public as well as the HCI community, possibly to the relevantly recently increase in availability and quantity of commercial BCI devices. This generates a greater need for knowledge in the design of these systems. However, following the same principles of brain-computer interfaces, it is also possible to design direct channels of neural communication interpersonally from brain to brain, creating what's known as a brain-to-brain interface. Yet, in contrast to brain-computer interfaces, in general, brain-to-brain interface technology has received relatively little attention. One of the first examples of a working brain-to-brain interface was a system presented by Rao and colleagues, in which the author on the left thought about moving his arm and sent this as an EEG signal from his brain over the internet to the computer of his colleague on the right, which was then sent as a magnetic pulse to his brain, causing him to move his hand and press a button on a keyboard. Now, since this proof of concept, there have been a number of other brain-to-brain interface systems following the same principles. However, to our knowledge, they all employ transcranial magnetic stimulation to send information to the brain. So this is a rather large and expensive, bulky device which ultimately bounds brain-to-brain interfaces to a lab-based setting, accessible only to well-funded research groups. However, there is potential for an alternative in transcranial electrical stimulation, or TES. TES is much cheaper than TMS, with many devices commercially available, some having an extremely small form factor. So TES devices stimulate the brain by rendering the brain as an electrical load in a circuit, which leads to a very broad generalized surface level excitation or inhibition of the cortex at the stimulation site, depending on the direction of current. And resultingly, while TES lacks the accuracy and strength of something like TMS, like it won't be able to actually move your hand, TES can induce a very general change in cortical activity, which can produce subtle effects such as changes in alertness or motor reaction times and other cognitive processes, all depending on what area of the brain is stimulated. The current can even be set to alternating current to produce an even greater range of effects, like modulating the firing frequency of a certain brain area, thereby entraining oscillations in a brain structure. Another effect of this is also to produce flashing lights in the user's field of view, or what's known as a phosphene, which match the frequency of the alternating current. So with these properties considered, we reasoned that a brain-to-brain interface system using TES would, rather than enabling transmission of very specific information like move right arm, would be more suited to transmitting vague and general cognitive states, like the feeling of concentration or relaxation. Which led us to realize that TES-based brain-to-brain interfaces would be well suited toward augmenting interbrain synchrony by matching cognitive states between connected users, with interbrain synchrony being the brain's natural tendency to synchronize between people when engaged in interpersonal activities, hypothesized to be a driving factor in humanity's ability to coordinate in groups. So considering these points together, we realized there was an opportunity to explore a novel class of brain-to-brain interfaces focused toward interbrain synchrony, so in an accessible and wearable form factor, and thereby allowing us to study the user experience of such technologies in the wild rather than in a lab-based setting. Which led us to the research question, how do we design synchronizing brain-to-brain interfaces to be experienced in the wild? Now, we answered this through the design and evaluation of a novel system, PsiNet.
Interbrain synchrony describes how brains tend to synchronize when people interact. This synchrony enables empathy, coordination, communication, and deep personal relationships. Many of today's social technologies ironically isolate us from each other. We believe with the right technology, we can be closer. We present PsiNet, a novel system we have designed to amplify interbrain synchrony. PsiNet uses brain-to-brain interfacing and artificial intelligence to sense brain activity in groups of people and stimulates their brains in response to be more synchronous. Participants wearing PsiNet can go about their day while the system monitors and stimulates all group members to increase synchrony. Through studying how people use PsiNet in their homes, we found that PsiNet can help people feel part of a whole, with greater awareness of others in the group, while also learning about their group through experimenting with the system. We intend that our work gives guidance towards a technological future of empathy and unity.
PsiNet consists of an ultra-cortex BCI headset housing 16 dry electrodes connected to a OpenBCI site-on board. So EEG is sent from the board via Wi-Fi to a Raspberry Pi that is worn by the user for data processing and cognitive state classification. So cognitive state classification is then sent to a server, which reflexively triggers the worn TES system to stimulate the user's brain through sponge electrodes via the signals from the Raspberry Pi. The system was capable of making 7 different classifications of cognitive activity and 4 different brain stimulation patterns. In greater detail, the system first classifies the cognitive state of each participant through an event-related desynchronization analysis on each of their EEG signals. This creates a matrix of states for each participant in the group, where a cognitive state is either present or absent. This matrix is then being sent to an intelligent stimulation control agent on a server at our lab. Based on the cognitive state matrix, the agent then decides which stimulation to give each participant based on what it thinks will most likely increase the group's overall interbrain synchrony, with this decision governed by this weight matrix here on the right. These 2 matrices are then multiplied. The product of this multiplication is used to determine what cognitive state the agent should focus on for that participant, represented as the highest value in their row, and what corresponding stimulation they should be given, represented as the highest number outside of the row, producing a final matrix of detected cognitive states and stimulations to perform for each participant, with the system then stimulating each participant. After stimulation is administered, the system collects another example of EEG activity and then compares this to the EEG activity just before the stimulation. The system then calculates whether or not interbrain synchrony has increased or decreased after the stimulation. In this example, the system is successful in increasing interbrain synchrony. If the stimulation was successful, the system then rewards the state-stimulation pairing by increasing their weight on the initial weight matrix, making it more likely to pick this pairing in the future. This loop continues throughout the duration of participants wearing the system, with a 15-minute cooldown after each stimulation. We evaluated the system and its user experience through an in-the-wild study, including 3 groups of 3 participants. Participants took PsiNet home for 3 days, in which they were free to make open-ended, unrestricted use of the system. In analyzing participant EEG, we found group interbrain synchrony showed a general overall significant increase when making comparisons between before and after the presentation of stimulations. Yet we note there was a very small effect size and suggest to take this result with a grain of salt. To understand PsiNet's user experience, we conducted semi-structured interviews with each participant at the end of their 3 days, with interviews then transcribed and analyzed via thematic analysis. This ultimately produced 3 themes. The first theme, dissolution of self, concerns how participants experience an altered sense of ownership over their own psychophysiological processes. What that means is that while participants were wearing the system and reflecting on how they were feeling and thinking, they weren't sure if their cognitive and affective processes were their own endogenous, unaltered processes, or if they had somehow been influenced by others in the group. The second theme, hyper-awareness, describes how the system promoted a heightened level of awareness toward their own feelings and those of the group. So participants reported that due to the presence of an ongoing open channel of information exchange offered by the system, participants were reoccurringly reminded to reflect on their own feelings and that of those in the group, and their gestalt relationship together. The third theme we uncovered was that of relational interaction, which describes how participant experience of the system was influenced by the relations between elements within its context of use. So often participants use their observations of what their other group members were doing in contrast with how they were feeling to help them reflect and make sense of why they felt the way they did. So this often resulted in groups purposefully experimenting with their environment and subjecting themselves to different activities in order to elicit responses from the system for them to observe. So considering these themes in conjunction with our own craft knowledge gained through developing PsiNet, we also offer 3 design tactics intended to guide designers and HCI researchers in the development and exploration of similar systems in the future, which you can read in the paper if you would like to know more. And with that, I conclude our talk. So you can find out more about what we're up to by either visiting the Exertion Games Lab website or my own website, and please feel free to contact us if you have any questions or are interested in collaboration. Thank you.